The following section is dedicated to fundamentals of simulation modeling. We're going to explore basics and fundamental issues about modeling. But I would like to pay your attention that the following basic or fundamental issues are really very important to understand all the next things we are going to discuss. One of the important keywords which we need to catch up is the concept of system. So, meaning that if you would ask the Google or if you would ask ChatGPT what is the system, most probably you will get a set of different definitions. That's why, considering that the word system is indicated as a keyword, we really need to catch up what is the system. So try to look to the following four definitions of what is a logistics system, what is a transport system, what is a traffic system, and what is a production system. Just stop for a while and think what is common between all the four definitions which are listed here. Now let's try to formulate a more generic definition of what is the system compared to what you have just saw. So first of all, and I hope you really catch up, that all four definitions indicates or presents that they are consist from set of items. In overall, we are not going to discuss a lot how to call them. Are they items or are they objects, elements, or subsystems? So I'm going to use a generic word items. So to have a system, what we need to do, we need to add that each of the item here has its own specific function or functions. Moving forward, we are able to state up that most probably, if we are talking about the system, we are able to observe an interaction between the items. And now a very important concept which we need to add here, that items which are interacting and which have their own functionality exist in internal environment, and outside is an external environment. Therefore, we are able to state that each system has its own boundaries. And this one moves us to the next concept, which is really very important for understanding, that if we are able to observe that internal environment is able to communicate the external environment, or vice versa, external environment is able to impact internal environment. In this case, we are saying that we are dealing with open system. If such interaction or communication is not possible, in this case we are saying that we are dealing with a closed environment. And finally, the last component to have the system, which is very important thing, we need to catch up that the interaction between the items, operation of each of the item is happening because we would like to reach some specific goal. So now I believe we are ready to formulate what is a system in frame of our course. So as you're able to see, of course, a system consists from interacting elements. Of course, we are considering that each of the item has its own function or functions. In the same time, this aspect is really very important for our course. We are recognizing boundaries of the system, so meaning that we are differentiating internal and external environment. And the final element which we are including in our definition is existence of the goal. So why operation is happening. We have defined what is a system. But before, it has been stated that we are utilizing simulation for complex system analysis. So what is the complex system? It seems that the complex systems combine interdependent elements, often organized hierarchically and decomposable into subsystems. Their dynamics are non-linear and shaped by feedback, adaptation, and self-organization. A key feature is emergence. So system-level behavior appears from interaction and cannot be explained by individual components alone. A following picture, which you are able to recognize here, demonstrates very well the concept of what is the complex system. Just try to explore and have a fun. Meaning that a beaver here is, it seems, impacting one specific element of the system. So a work is done, and only after we are able to recognize that actually a system was complex, and the impact, at least in this case, would be really dramatic one. In many real-world cases, such as transport networks or logistics systems, direct experimentation is expensive, risky, or maybe simply impossible. Instead, we represent the real system using a model, which acts as a black box. Inside this model, we define rules and logic, for example, how vehicles move through a network, or how orders are processed in a warehouse. We also set parameters such as demand, fleet size, or processing times, and make assumptions to simplify reality. By running experiments on the model, we can test different scenarios and use the results to improve, for example, traffic flow, reduce delays, or optimize logistics operations. The same concept can be demonstrated using the following picture. So as you see, in a real world we have a system. So we could imagine that, at example, this one is a supply chain. So what we are able to recognize that probably we have an issue, we have a problem. People, probably our customers, they are unhappy. So what we are able to do, we could introduce some changes. But remember, we are dealing with a complex system. So meaning that we are not able to predict what will be the impact of our changes. Therefore, a modeling theory saying us that please don't do it. This one is very risky. So instead, what we need to do, we need to leave a real world and we need to move to a world of models. So what does it mean to move to a world of models? It means that we need to construct the model. So the model is a simplified representation of the real system. And why actually I like the following picture, that you are able graphically or visually recognize that here is the real system, here is actually how the model looks like. So it's a map, we could see the item, we could see an interaction between the items, but we are not able to see trees, specific people, road, vehicles, or whatever. So what the previous definition stated to us, that having the model we are able to do any kind of experiments, probably we have some ideas of how to resolve the issue. So this one would give us a solution. For example, optimized supply chain. and if we have constructed the model in a correct way, this one gives us ability to apply received knowledge to the real world system. And again, if we did everything in a correct way, we will get an optimized real system. There are many ways to represent and study systems. In this course, we focus on mathematical models. Some of them can be solved analytically using equations. However, when systems become complex, stochastic, or large-scale, analytical solutions are often not feasible. In such cases, we use simulation models, which allow us to experiment with the system behavior in a controlled and risk-free way. Here we compare analytical and simulation modeling. In analytical modeling, the system is described using equations. Inputs and parameters are linked directly to outputs through a mathematical function, so the result is obtained in a single calculation. This approach works well when the system is simple enough to be solved analytically. In simulation modeling, instead of solving equations, we reproduce the logic of how the system operates over time. The model runs step by step, applying rules, parameters, and randomness, and we observe how the system behaves under different scenarios. This makes simulation especially useful for complex logistics and transport systems, where analytical solutions are not feasible and experimentation in the real world would be risky or expensive.